Good day. Today I would like to present my research project related to modeling demand response systems in the energy market. The integration of the energy market paradigm is growing rapidly, and so far, there is no doubt that it will completely replace the traditional, centralized paradigm of the electric power system in the world. But due to the specifics of the decentralized architecture of supply and demand systems, the integration of this technology entails some engineering problems. For example, each individual node of the demand response system must be smart and partially autonomous. Connecting a node to the global energy system is more difficult than in the case of a centralized power distribution system. The communication between the nodes of the demand response system is not rigidly standardized. Therefore, there are already several large players in the energy market area. For example, the IEEE 61850 standard, OpenADR and OCPP. And in theory, they both can operate in the energy market at different levels. Distributed systems are more difficult to model and analyze. Mainly, because the objects that being modeled can be far apart, and because of this, many additional parameters start to play a significant role in the simulation. As an engineer, I would like to have a tool that can provide me with a complex set of data, some set of system measurements and configuration files. I mean not only some files which for example uses the IEEE 61850 standard, but also real project files, like executable for the PLC hardware or the application file for a PC, that can be deployed, or installed, in a real hardware. Let's say I have a residential area, where electricity consumers are quite deterministic. Each house has an oven, lighting system, TV, computers and similar. But the number and types of electricity generators can be very diverse. One house can have a solar panel on the roof, in the other house, a small wind generator can be using, and the third house may has no electrical generator at all. Since the system under study can be highly distributed and diverse, it was decided to develop a simulator bench, which should also be decentralized and easily reconfigurable. So here is the essence of project. I have a residential area model that works in MATLAB Simulink. This model is deployed in a hardware in the loop simulator. Using OpenADR hardware extensions, digital and analog outputs and inputs, and its communication ports, I connect my virtual model to other hardware. For example, I developed a power flow control algorithm, implemented and deployed on a PLC. In addition, I have connected two BeagleBone devices that take analog signals from OpenADR, and I have a simple power management application, something like a simple SCADA, deployed on the PC to analyze the data and control the system. The composition of the test bench is shown in the diagram. As a result, I would like to demonstrate how this type of system works in reality. Let's say we have a power system model implemented in MATLAB Simulink environment. We can deploy this system to OpenADR and run it. Since the capabilities of the 61850 standard are already integrated into OpenADR, we can use it to control the message flow directly from the MATLAB project. So, when we run our model, some measurements of the simulated power system, along with 61850 protocol messages, are available for analysis. We also connected two IoT devices. The first IoT device converts analog signals into messages, according to the OCPP standard. The second IoT implements the same functionality, but for OpenADR protocol. So, if we want to activate testing of OpenADR or OCPP functionality, we only need to activate the corresponding devices, and that's all. As an intermediate result, I can say that I have a tool, with the reconfigurable specific. By using such a test bench, it is also possible, for example, to simulate and test various types of communication protocols. With the help of this tool, I can get the following practical information about simulated system. The theoretical amount of energy produced and consumed under various conditions. During a short-term simulation, investigate the behavior of the PLC as a control tool. Check for errors in the control algorithm, or possible shortcomings. During long-term simulation, it is possible to investigate the resistance to failure of the developed algorithm. For example, I can collect information about the signal latency of PLC, and then analyze this data. I can find the minimum and maximum values of signal latency, mean and quantile of 75. Check and debug the configuration file with the CID extension, both for the server and client sides, find possible flaws and inconsistencies before actually using it in reality. Check the algorithm structure of the energy management application to find some bugs and shortcomings. Summarizing the idea of my project, I would like to say that my main intention was to develop a distributed modeling tool capable of providing information from various aspects of the simulated system, from measurements to real examples of executable files for real equipment. Thanks for watching this video.